Guys, this is Mr. Lon here talking about PES, and let me move my face here a little bit. Alright, so we're going to talk about PES real quick, photo electron spectroscopy, so make sure you take out your notes and let's get started. So before we start on PES and what PES is, let's talk about the various models of the atom. So at the beginning, Dalton came up with this idea that, the atom was really just singular. There was nothing, no subatomic particles that came about, and in fact when he first came out with this model, he basically organized the elements according to this atom. So it's a very crude way of writing things because they didn't really know about these subatomics. Then came J.J. Thomson, which did an experiment here where he was basically taking a look at the model, and here he introduced electrons in, and so this kind of got revised and improved on Dalton's existing model that all matter is made of atoms. Rutherford then came in with his famous alpha beam gold foil experiment, where he shot these alpha beams into the gold foil and take a look at what happened when they got in. Now these alpha beams were positively charged particles, and what he found out was as you were shooting through this alpha beam, alpha foil, you ended up with some sort of deflection, indicating that the center of the atom was made from this positively charged nucleus and mostly empty space. Then Bohr came out, and Bohr really kind of set the stage for the organization of electrons in these things called orbitals. And Bohr basically was able to figure out that, each electron as a jump, they begin to emit specific types of light. And this has to do with this idea of energy levels. And so if you're able to quantify where these lights are coming from and what type of light they emit, you should be able to determine where these electrons are located. So Bohr really kind of set the stage for this idea of orbitals. Now, moving along with electron configurations, we already know that electron configurations have these orbitals according to Bohr's model. So if you take a look at energy levels, starting off with the 1s, which is the lowest one closest to the nucleus, all the way to your higher ones, like for example your 8s, you can kind of see that the way you read this is you go 1s, 2s, 2p, 3s, 3p, 3d, and you begin to start noticing that there's a pattern that as you get higher up to the configurations, each one's going to hold a different number of electrons. And so the last line here, it's 5f, 60, 7p, and 8s, you can kind of see the d orbitals are going to hold 10, the s orbitals are going to hold 2, and the p orbitals are going to hold 6. So if I wanted to fill in these electrons, what I would do is I would try to fill in as many as I can based off of this idea of electron configurations. And so once you get down to your 8s, now your 5f and your 60, 7p, and 8s, things don't really follow the same number anymore. But again, indicating the placement of these electrons is important. So here is basically the all elements kind of follow the rules of which blocks there are. So if I take a look at these blocks, group 1 and group 2, they are going to be your S block, meaning that they're going to have in their valence electrons s orbitals filled in. So if they're in row 2, they're going to end up in 2s and 2s2, 3s and 3s2, and so on, while you get the p block on the right hand side, with the exception of helium and hydrogen. These are going to be your 2p blocks, and basically they're going to be filling up the same way. Your D block is your transition metals, which are going to have up to D10, but they're going to be filling up depending on the row they're at. So here we're in row 4, or period 4. However, if we're actually not counting the first row here, we're counting this one, this will be your 3, your 4, your 5, your 6. And then your 2 lanthanide and actinide series are going to end up with the F blocks. Now, this is actually on the 4, so if we take these two, just imagine that they are actually inserted into these two rows here. So you have your 4 and your 5F blocks. Now here's an example for chromium. Chromium has 4s1, 3d5, and the reason why is because you take a look at chromium being a transition metal, so chromium has to be, in the D block right here. While copper is also a 3d10, it's in row 3 right here, if you're not counting the first one, and it would have same thing, it would use argons, and then you would have your 3d10. So the difference between chromium and copper is pretty much 5 electrons, and so we see that how it got filled up on that D orbital from 3d5 to 3d10, and everything else is the same. Now, what do we know so far about spectra? Well, the first thing is, if you take a look at these lines, it indicates the frequency of that wave or color. So red being, the lowest in energy would have a larger wavelength with something like a blue. So if I take a look at these four lines, it could tell you which orbitals are coming in from. So if I shine an electron and it kind of bounces and it rises to another one, I'm putting in some energy in. And as it rises, it falls back. And once it falls back, it's going to end up giving up a specific type of energy. And you can do that calculation with this formula here to figure out what that's going to look like, as long as your z value is equal to 1. Now, for all intents and purposes, you just basically have to know that energy, as it drops from one shell to another, emits this type of energy, which you can eventually determine the exact type of electron that in that shell. Now, ionization energy really falls under this idea that if you want to remove an electron away from its current shell, you have to apply some sort of energy in it. And Z value is an atomic number that we're talking about here, as long as it's going from 0 to 35. And as you can see, if you have something like helium, helium is actually really, really hard to remove. In fact, helium has a 2.5 energy here. And the reason why it's so difficult to remove is because helium is basically a noble gas, and it's in group period 1 from the periodic table, which means it only has 2 electrons total, and it's not going to want to give away those electrons. Something like neon, same idea. So usually your peaks are going to be your noble gases, but as you go down a group, you can kind of see that the ionization energy level kind of drops. So lithium compared to like a hydrogen, lithium is in group 1. You can kind of see that it would definitely lose. It would actually be very easy to remove that electron. And so that's the general trend you'll see, is these peaks kind of going down, and it's going down across as you increase the atomic number. Now, to give you an idea, if you take a look at lithium here, lithium is located in group 1. It only has 1 valence electron, so it's not going to really care if it loses that electron. So the ionization energy is really low. But if you go across, going to neon as an example, lithium to neon, you can kind of see that at that point the ionization energy very drastically increases. And same thing with krypton. Krypton is actually here, but as you go down a group, that's where the ionization energy definitely starts to decrease as you're getting down to like your rubidiums and your cesiums. Now, taking a look at your ionization energy values, you have multiple IE values, what they call it, level 1, 2, 3, 4, 5, and so on, indicating how many electrons you're removing from the orbitals. So on the first electron that you're removing from sodium at 495, it's pretty straightforward. 495, not too bad. But then you get to your second electron, and now it costs you almost 10 times as much. And the reason is quite simple, is because sodium already has a full octet by the time you remove 1 electron away, and it's going to cost you way more. So you know that if the IE jumps to almost like a 10-fold increase or a 5-fold increase, that you've already hit a full shell. Now magnesium, it's the same idea. Magnesium has 2 valence electrons. From the first one at 735, removing the second one is pretty hard too. But if you go to the third one, now it almost jumps to a 7-fold. So at that point, you know that this has to be magnesium, because by the time it jumps to your second IE, it actually has that. Now, moving along the line, just taking a look at the same pattern with phosphorus, right? So phosphorus, you see that big jump by your 6th electron. And if you go back here to the periodic table, you can see that phosphorus is in group 5, which means it has 5 valence electrons. And pretty much, if you take a look at phosphorus, 1, 2, 3, 4, 5, but if you hit the 6th one, then that's when you get the problems here. So you know that the full shell starts at IE6, or the 6th electron. Same thing with sulfur. Sulfur here has, and here's just to indicate the jumps here. Sulfur has the same problem here, when you get down to 7, is because, most of the numbers are pretty consistent across the board, but when you get to IE7, you end up with that, and we already know that because sulfur is in group 6. And so basically for learning target 1.5 and learning target 1.6, you're able to explain distribution of electrons in an atom based off of data. So I'm able to tell in which group this one is based off the IE values, and also be able to identify the relationship between energies and patterns. So as an example, we're taking a look at the big patterns, the big numbers that you see right here. IE2, IE3, IE4, IE5, and so on. All these big numbers tell you that this has to be in group 6, this has to be in group 5, this has to be group 4, 3, 2, and 1, and so on, because to remove that extra electron would cost you way more energy than normal. So how do we take a look at this? So we talked about the energy being your Planck's constant times the frequency, and we take a look at, how you're able to tell, the energy. So microwaves, usually the way it works is when you apply a microwave to an atom, it rotates. In an infrared, you vibrate. So the molecules would actually move up and down versus moving in a turn. In a visible light, electrons are transitioning. Basically, you have electrons moving from orbit to orbit. Same thing with UV. And in X-rays, really interesting is that when you actually apply an X-ray radiation, the core electron transitions in the atom. So the very inner core electrons tend to jump, and that's why X-rays tend to kind of cause a lot of damage in these type of things, is when they release that, you can kind of tell that they actually have some sort of a lot of energy able to jump. Okay, so if I apply any sort of light for this, you're able to move these electrons again. But microwaves generally will just move the molecule. They wouldn't really actually technically pop electrons out. If that were the case, we wouldn't be using microwaves. And then if you calculate that energy values, you can calculate it using your IE, so H times V, to calculate your kilojoules per mole. And then as you get larger to the 0.495 million joules, then that's where you're getting into the larger numbers for IE as well. So you can convert this to millions and kilos. Okay, or megajoules. And what you have right here is basically this idea. Valence electrons are transitioning to the atoms. So UV has a lot of energy, as you guys can tell from this, based off of the hertz and also based off the energy. That's why the energy is so high. So apply that, you can kind of see that the electrons are going to pop out from the UV rate. So how to remove core electrons? Basically, you apply the energy, and if you have enough energy like a big wave, you can basically calculate that out. So if I do the conversion, it's times 10 to the 8 joules. That's a lot of energy. Then you can calculate the frequency of that by dividing your energy divided by Planck's constant, and you can determine the frequency of that, of how fast this thing is going. So that's a pretty fast electron that's moving out. And then you can calculate your Vmin. And as an example, taking a look at X-rays, X-rays have a lot of energy, a lot of speed, and that all has to do with the energy being put out. So here's another example. We apply some energy for the core electron, the electron flies out, and then you can kind of see those specific ones. Alright, so let's talk about the PE instruments real quick, and how do you measure the electrons as they're getting popped out when you apply a specific type of energy in it. And the way we do this is we want to remove core electrons, and we also remove valence electrons and so on. And so usually you have a couple parts of this PES experiment. You apply some energy in it in these areas of this machine, and usually you try to analyze how fast the energy is as you're moving through this. So let me go ahead and explain this real quick. So there's this thing called binding energy or ionization energy, how much energy that's actually binding to the core nucleus. So all these electrons are kind of rotating around this 3+ core, and as you're applying an X-ray or UV source, you're going to remove the core electrons away. And as you can see, as you're removing these electrons, you're beginning to see spikes on this graph here. And this shows you that this is going to be your 6.26. And then you get another electron that kind of pops off the second line, and that's your 0.52. And more electrons get popped out. So you begin to really tally up how many electrons are getting removed from each of the orbitals. And so you can see the 6.26 getting larger and larger. And you can see that as time goes on, the more of these beams that you apply, eventually you're going to get a point where you're going to start seeing higher spikes, and those higher spikes indicate how many more electrons you're actually beaming out. So the analyzer, the kinetic energy analyzer, is going to go ahead and measure those, and without going into detail, basically it's going to have electrons coming in. The more negative voltage are going to be here, and the light negative voltages are going to be down here, and they can measure it out, and there's a whole section that goes with it, and we're not going to spend too much time on that part. Alright, and then, taking a look at boron as an example. Boron is going to get popped off here. We're going to get 19.3 and 19.3, and you can kind of see that boron has 3 peaks. while lithium only has 2 peaks. And so that kind of makes sense, right? Because if you take a look at how many electrons are getting removed from all of its shells, right, you basically are going to have to figure out how many electrons you have for each one. So let's take a look at analyzing the PES data real quick. So here's an example of one PES data. So this one we have 84, 4.7, and 2.0 as an example. And we have a binding energy right here at the bottom indicating, now remember the graph is reading from right to left, so the higher numbers are right here, and this indicates how many electrons you have. So here we have 2 electrons, and here we have, if you count each line, is 1, 2, 3, 4, 5, 6, and then 2. Alright, so the question here is, what orbitals are we looking at? So because it's a 1s orbital, and it's an 84 right here, that means it has a very, very high energy usage. So that means it's probably a 1s orbital, which means that the binding energy it takes a lot of energy to remove it because it's so close to the core. Then we look at our next one. So what's after 1s? Well, it's got to be 2s. And 2s is going to be a 4.7. The reason why it's 4.7 is because it's a little bit farther out. So 2s is a little bit farther out from a 1s, but we only have 2 electrons in there. And then your last one should be your 2p, because after your 2s comes your 2p orbital. At that point you have more electrons. So the question here is, which of the following elements might this spectrum represent? And so it's a pretty straightforward here. If you add up the electrons, you definitely have a 1s2, 2s2, 2p1, 2, 3, 4, 5, 6, 7. So we're looking at, in this case, going to be neon, because neon has a full shell already. So here we have 6 lines, which is 2p6, 1, 2, 3, 4, 5, 6, 2p6, and that would have to be neon. So that's a very classic example of an AP problem that you're probably going to get. All right, let's see if you can do this example here. And so pause the video right now if you want to try it out yourself to figure out what element that would be. And so the question is, identify the element based off of that. All right, so we have a couple of choices here. We have boron, aluminum, silicon, and sodium. So let's take a look. All right, so basically same idea. We have to figure out how many relative number of electrons we have. So if I indicate this 1s2, 2s2, 2p6, 3s2, and then 2p1. So in this specific case, if you have 1s2, 2s2, 2p6, 3s2, and then 3p1. I think I said 2p1, 3p1. So this actually has to be in obviously your period 3, and it has 3 valence electrons. So that would have to be, boom, aluminum. Okay, because aluminum has those 3 valence electrons in period 3. All right, so here's a real life example of a PES graph, and as you can see from here, this is how they kind of use that in real life. They talk about how many electrons you have, the intensity. Now normally they have intensity values instead of electrons, but you know, just to show you guys the different types. All right, and here's another example of just something that they see in copper versus chromium. Okay. All right, guys. Well, if you want to know more about this and you still have any, we'll do some practice problems. But thank you for listening, and I'll talk to you guys later.